Hi, welcome to this movie about Scribble and distributed systems. In this movie in particular, we're going to look at how Scribble maintains the velocity of value against a rising pace of change. So the idea here is that we can maintain the cadence of value creation even whilst complexity increases and we have to consume more and more change. We'll show how Scribble minimises integration errors, how it can reduce the cost of the complexity, how it can increase the speed to value, so the speed with which you can deliver software solutions to the problems that you have, and how it can increase the quality of the value that gets delivered, all in the context of building a microservices architecture, not from the very beginning in a greenfield, but rather within the realities of life that we find ourselves, where we have a number of heterogeneous sorts of systems. And we will look at the roadmap as to how we can go from one kind of architecture to a microservices architecture. So we're going to do this by looking at the evolution of enterprise systems. So we start off with a client-server arrangement, where communication is often point-to-point. It might be by file exchange, it might be through some sort of IP digital transfer of data, or it might even be through a shared database of some description. So you tend to have bespoke clients, and the deployment is really by domain. So as a domain changes and collects all the changes, so deployment occurs. So you're having to wait and synchronize all of the deployments of the different pieces of value that you want to deploy. The cost of these sorts of systems generally is twice the number of servers, so that you've got a replicant, times the number of environments. So you might have dev, you might have test, UAT, you might have SIT, pre-production and production, or you might have factored some of those together. And the number of clients is the number of users times what effectively is a fat client. So it has to have a bit more processing power than a browser, for example. So then we move on to the next kind of distributed system that we found later on, sort of really in the late 80s, early 90s. Message bus tended to connect the servers that were running, and deployment was by functional area within the domain. So the server would often just be a functional area, or you might have a number of separate processes running as different functional areas, sharing some storage. But it's effectively, the difference was that you were decomposing things into functional areas within a domain and deploying on the basis of the functional domain, so you could deploy smaller units of change and therefore increase the pace. Sharing was through back-end message buses, so one server might talk to another in order to synchronize some information. This was all really sort of the rise of SOA and ESBs. Number of replicated servers is times 2. Number of environments, often a shareable factor, because you might put all of the functional area services within a domain on a single box, so you can get some sharing that way. And it's times the actual number of users, again for fat clients. It's just that they're a little more integrated this time, with some sharing of screens and so on and so forth. And deployment by function area within domain. So the idea of microservices, of course, is that you might have a message bus, you might have JSON on the wire, tend to have browser-based clients, and the incremental deployment is based on what's called bounded contexts. And so the bounded context might be the delivering of some value, so some small piece of computation that's required. So there'll be some sort of HTTP connection possibly to the client, and that value will be transmitted using kind of RESTful API. And this is why we associate APIs with microservices. So the bounded context fully fledged might be all of these 5 microservices. It's pay by process at lower cost per MIPS because you can deploy in a cloud, much more horizontally scalable, lower cost per message, lower cost for memory, and the number of users is, or the number of clients is the number of users times thin browser-based clients, and the benefit, of course, of mobility, as we can use HTTP5 across a cellular network and receive it on our phones or mobile device. So that's kind of how the evolution of enterprise systems kind of works in a nutshell. We might just deploy the one piece of value initially, and then gradually do all the others. So a typical way that we would take an existing legacy, so on the right you've got the legacy, might be to slice a bit off with a bounded context, and then we have to develop that. So somebody sits down, does all the wireframes and all the rest of it for the client, and the architects who are in the room sort of elicit some sort of sequence diagram that says these are the components that we need to build, these are the ones we need to talk to that currently exist, and the journey towards microservices begins with potentially each of the swim lanes representing a particular microservice. That's how it begins, and then we go through and subsequently pick off each piece of value until the whole bounded context is done. It doesn't have to be the reverse order, it could be any order. It's the order that's most applicable to the business in terms of the value that you get. And as a result, value gets created much quicker. You start to build up a bit of momentum, slicing off different ones. And so you shrink the old total cost of ownership as you embrace that new model. And over time, you get ever more, and you're much faster at being able to deliver change. As the dependencies decrease and you uncover the bounded contexts, the ops costs drop because you use DevOps and CDCI, so you can deploy very rapidly, further shrinking the total cost of ownership. And eventually, stateless read services scale well, so we get really great scale for our data that we want to share with the world and do business transactions. Still hard to get stateful done quite as fast. They're a bit more complex. SIT testing much faster because of the DevOps and CDCI pipeline environment, but more complex with a lot more chatter between the services, a lot of chatter. These services are choreographed, they send messages to each other. So it gets a little harder to do the SIT testing as you get bigger. And so eventually the velocity starts to tail off as that complexity in the chatter grows. It becomes a little harder to monitor at the business level because sometimes the bounded contexts, particularly when you're doing it in stateless idioms, seems to be much further away from the business domain in terms of how one might consider a particular microservice. And so it gets a little trickier to monitor across all of the microservices as they're executing. However, the bet on the good side, whilst that's going well, shall we say, even with a little complexity, the total cost of ownership of your old real estate is shrunk, and you should be on a much better model in terms of the costs because you're using Cloud Venue. So over time, the number of processes gets into the thousands. I mean, this is just a small graphic. And all the services are instantiated, so the runtime costs you incur, some of it is actually without any value. And yet the microservice architecture is very flexible. It would be very useful if we could only pay for what we consume. A microservice could be sitting there, not get used, because the microservice before it decided to do something else. But you're still paying for some, let's call it residency costs, rather than processing costs. And that mounts up when you've got thousands of these things, and thousands and hundreds of thousands of transactions. So it'd be nice to get some efficiencies from a microservices architecture that allows us to be a bit more selective about what's instantiated. And, so the total cost of microservices is really the total number of microservices times the residency plus the transaction costs on top, amortized over the entire set of microservices that really should be generating value even when they're not. So it gets even worse when we start to factor in IoT. So now you've got zillions of these things. So you've got a lot of IoT devices out in the real world, data being consumed by some of the microservices, computation happening, value being delivered to clients, and so on and so forth, as we're trying to figure out new business models. But the cost, is starting to get pretty high. And all that data, all that data through them terrible. So this is what Scribble could do. This is what Scribble could do. So we're going. Okay, so in the demo, we're going to look at a requester, a login service. The requester talks to the login service to get the login details, which work or don't. A bunch of other services that are made available once you've managed to log in. So there's the authorization service, for instance, that goes and forwards your request, gets the real data, comes back, does a filter to remove the data you can't see. And that's kind of the context of the demo. It's sort of loosely based on a large retailer and how they want to interact with their suppliers. So we can write all the sequence diagrams as this piece of Scribble. So we've got a partnership supplier protocol, call that an explicit global protocol, because it's going to describe the choreography between the login service, the requester, the authorization service, filter service, supplier service and the contract service. First sort of thing we do, we send a login, and then there's a possibility of a choice here. Either there's a login failure or login successful, in which case the requester connects to the authorization service, just like in the sequence diagram. Eventually, if it fails, we recurse into the partnership supplier protocol, so there's a recursion built in. If it succeeds, connect to the authorization service, which connects to the filtering service, and then we do this sort of main bit. So in Scribble we can essentially have sub-protocols, as it were. So we've got this auxiliary, we call it, protocol, which does the main. So this, you can either get suppliers or you can get contracts, and once you've done that, you can recurse back into it, so it presents you with the same choices again and again and again. If you go get the supplier details, well, it might deny you, or it might say, yep, that's okay, in which case it connects to the supplier service and goes and sends your request onto the supplier service, and then it does this sort of fancy bit where it will pass the appropriate details in a sub-protocol called the filter, which is just below. Getting contract information, exactly the same pattern, and the actual act of filtering itself has this interesting method signature because it can be parameterized on a function, so it's kind of like a lambda approach to passing functions, and that's what does the filtering. So that captures all the use cases. I mean, we could be more explicit, we could put some error conditions, further error conditions, but generally that's essentially it. So what we're going to do here is we're going to run the generator, and it's going to generate all of the endpoints. It's going to generate them as finite state machines. So this isn't code we have to write. This happens directly from the Scribble. So we can pull up one of those finite state machines as an example. So if we pull up, I don't know, the authorization service, something like that, you can see. So here you can see the authorization service. There's essentially two paths. You're either getting suppliers or you're getting contracts. There's a bit of setup to do, but essentially that's the behavior of the service you want. So in a stateful world, this is kind of how things work. And then we do another one for one of the ones it has to interact with. So this might be the login service. So you either succeed or you fail. But essentially they're all, broadly speaking, get rid of my Wi-Fi, they're all broadly speaking the same in the sense that they can be represented as finite state machines. And the aim of the choreography is to capture the collective behavior of those state machines in a protocol without a biased view. And this allows us to decouple all of the finite state machines, safe in the guarantee that the behaviors are actually complementary and will obey the rules of Scribble as a dance. So that's it so far. What we'll do now is we'll start up some stuff and see how that goes. So I'm just getting my Windows ready. So what I'm going to do now is I'm actually going to execute each one of the services that we generated as a finite state machine. I'm going to execute them, so they're actually going to run. They're going to talk over sockets in this instance, so it's not a true sort of cloud deployed microservice, but a microservice it is nevertheless. So I'm just going to start them all up, and as you can see, given my sort of comedic bent, I wanted to make them sound like they were part of a game show. So tonight, Matthew, I shall be is what they tell me. and so they're telling us that they're playing the appropriate roles. So I'm just starting them all up. And the thing to notice here is that so far they all come up with command colon until this last one, which comes up with a question mark. So that tells me who's in control. So who's in control? It turns out, of course, it's the client in control. So tonight, Matthew, I shall be the requester as a client. So it's in control. It's got to do something. And we could imagine that that could easily be encoded inside a browser. So the browser would then be asking for input from the user, the requester. So I can select something. So I'm going to request a connection to the login service. And you can see that there's some messages that went up the screen on the login service behind us. So now we're going to send a message to the login service to actually do the login. Watch where the locus of control goes. The locus of control now, as you see, I've got some debugging in there, is now with the login service. So now I can send a message back. So I'm going to send success. And now you can see that this one has stopped. So I can get rid of that. And now we've got a request connection to the authorization service, the authorizer service, and the locus of control is back with the requester. So we carry on, we do that. As a result, this guy's got the request to connect to the filter service because he's got locus of control. So two things now can happen in parallel. The authorization service can connect to the filter service, now connected. Locus of control has now gone there, he's now waiting for something from somewhere else. And now we've got the requester with, do I get contracts or suppliers? So I'll do suppliers, just for the hell of it. So now I've done that, the locus of control has gone back to the, with the question mark, to the authorization service. And he's going to either request a connection to the supplier service, or he's going to check in the database to see, well, can this requester actually do this command anyway? And if they can't, then the business logic would determine that it's send a message to deny. And if you can, then it's actually going to connect to the supplier service because it already knows that you want suppliers. Now you can see that something happened at the supplier service. So it's now received the connection and it's waiting for you to send the message on. So the authorization service sends your message on to the supplier service, which now has the locus of control because obviously it's got to send it back. So when it sends it back, now we're going to send a message to the filter service because we're going to go filter the data, get rid of the JSON stuff that we can't do, that we're not allowed to see, which is what the filter service does. So we've done that. So now the filter service, or the supplier service, is doing something in parallel to disconnect, so it can disconnect. The filter service is now waiting to send back the filtered information to the authorization service, locus of control back to the authorization service, disconnecting from the supplier service, sending the message back to the requester, and now we're back to the beginning again. So that's showing you how easy it is to have a 5-node, fairly chatty, stateful set of interactions that just work. And they work not because I wrote the code for the finite state machines myself. I got a computer to generate it from Scribble. So one of the benefits of Scribble, and you're going to have to do a ... here, is imagine now these are the first versions of a set of microservice for a bounded context. And maybe just a thread through the bounded context, maybe it's not complete. So you can write the Scribble for that and stand these up in your CDCI environment and then use version 2 or version 1.1, however you want to do it, as having the binding of the business logic. But all the while, you can exercise all of the other chatty exchanges of information to do things stubbed out, but in the correct way, so you don't get any integration errors. And that's really one of the massive benefits of Scribble, let alone the ability to now monitor, do it the reverse way, monitor the messages that we see against the finite state machine descriptions in each case in order to ensure that they are conforming to the correct behavior if somebody actually implements them from scratch, or indeed to just simply be able to monitor it at a business protocol level. So there's many benefits to using Scribble in terms of making sure that we get good, robust distributed systems. And we can then change the Scribble over time. We can measure one piece of Scribble from another, determine exactly what needs to change, target our changes more effectively. And all of that is what reduces the complexity of change and with the velocity of change that we're facing, it reduces all that complexity and so enables you to deliver value at pace regardless of the complexity, because it's actually removing a lot of the plumbing, if you like, that really we don't want the developers to have to do. We want them to write the business logic. So in the next demo, we'll have a look at how that might look if it was an HTTP server. And we'll actually generate dynamically. So that'll be the next demo. So hope you like this one. Thanks for listening. Hi, in this next demo, we've essentially wrapped up the finite state machines that you saw before and put those into an HTTP server, which can really only do one thing initially. It can accept this message at the top. So it sends a Scribble file to a particular URL, particular port with a URI, and the format of the message is EPP for endpoint projection against the protocol name in the Scribble file for a particular role. So what we're going to do here is bring up an HTTP server which can only accept this sort of message. If you send it anything else, it will simply just ignore it and send back a 404. If you send one of these, what happens under the covers is the HTTP server parses the Scribble, so it uses the Scribble compiler to parse it and make sure the Scribble's okay, and then do the endpoint projection to create the finite state machine for that role within the Scribble. So you go from an HTTP server that only has one behavior, which is to accept an endpoint projection post, and it becomes an HTTP server for that particular role name with all of the finite state behavior that's commensurate with that particular role. And it does that automatically just by simply sending this message. So we're going to have a look at this in a minute. Once it's received that Scribble file and it's done the endpoint projection, so it's behaving as an HTTP server for that role name, then it can accept messages of a particular form. And that form can be whatever you need it to be. And it then cycles through the finite state behavior and accepts only those messages that it's allowed to. When it accepts on the client side, it responds and says, hey, I've done that. But by the way, these are the things I can do next. And on the server side, it gives you some narrative as to what it's trying to do, whether it accepts the message or not, and what its current next states are. So what it can accept as valid requests from some requester. If you try and do it wrong, so if something goes wrong, so classic case here, requester versus requester, it responds and says, hey, I don't have a matching state transition for that on the client. So the server responds with that message and says, here's the problem that we've got, which is very handy because these problems are actually quite tricky to get. You're really reliant on the developer sending back for the server, sending back the appropriate data so that on the client side you understand what it is you might have done wrong. Because at that point you don't know whether it's the client or the server. In this case it's the client sending the wrong message. And on the server side again, this is all inbuilt into the finite state machine stuff that's injected into the HTTP server. It gives you a narrative as to why it went wrong, why it couldn't deal with that particular request. And it leaves it in the previous state. Now, one of the nice things that you can do, if we go back to the EPPP, is that you can add to the role name, you can add the start state. So we can start a finite state machine in any one of the valid states, which means that if one of them dies and we need another one to pick up where the other one left off, it's really easy to do this. We just inject the Scribble, the protocol name, the role name, and add the state that we want it to be in, and it comes up in the appropriate state. So let's have a look at how this actually works. So I'll just put this away and we'll start up a server. We'll give it a port name and a URI. So the server's up and running. And here we will execute a range of different scenarios. So the first one we'll do is a straight test. So the first thing it will do is it will inject its EPPP message. So it's got that. So you can see that the server's now been instantiated as the authorization service based on partnership suppliers, so it's done its EPP load, and it's now waiting to accept a connection from the requester. And the requester, oddly enough, has seen that the state that the server's in is that it's now accepting messages. The message it can accept is an accept connection from the requester. So if we go over to here and we just press return, you can see that the finite state machine is going through its paces, and in each case the client's actually just sending a curl message in this case to actually send the appropriate message to the server, and it can go through the whole thing, and then it's back to the beginnings where it's really just waiting for either contracts or suppliers. And of course we can do exactly the same thing with the suppliers. So sorry, with the contracts. So we can check that that works too. It helps if you actually get this right. There we go. So now it's happily going through all the messages for contracts, and again it will get back all the way to the point where it's ready to receive either a request for contracts or a request for suppliers. And if we do the same thing with errors, Scribble demo API, we'll see that the first message it's going to send is going to be wrong. So if we get this right, yeah, so we can see that it's wrong, and it's wrong because it sent a message, I think, for requester and not requestor. So we should be able to see that up here. Yeah, where are we? There we go. So you can see here it's got requester and not requestor, and that's what's really sort of meant that it can't understand what the message is. So it says, hey, I've got an error. I've got a receive message, get contracts from requester, has no matching state transition, and it responded back and said, hey, look, I don't understand this. This is what I can receive. Please send me the right message. So in a sort of development environment, if you're developing your microservice and you want to make sure that you're sending all the right things to other microservices, or that you're receiving the right things from other microservices, or indeed from a UI, having this level of automated logging based on state behavior, which is just a structuring mechanism. It's no different to sort of the structuring mechanism you have in ordinary programming languages that help you understand the program. This is just helping you understand the dynamic behavior of a number of finite state machines. It gets you there far quicker. You can't make errors in the same way that you could before, because the finite state machine machinery won't let you, and the Scribble description is what's driving that. So ultimately it's the Scribble that's driving the structure here on each of the finite state machines, and therefore ensuring correct behavior all of the time. So I hope that makes sense. What's next to be done is to containerize this using probably Docker, test it in an execution venue, and test the outbound messages from an HTTP server that's trying to contact another server. And by doing this, if we can do the dynamic invocation of the HTTP servers as well in Docker, which I believe you can, we can get this lazy instantiation of finite state machines, just as we postulated right at the beginning. So I hope you've enjoyed that. I certainly have.